Welcome back. We'll next hear from Soledad Villar, who will be discussing machine learning and symmetries.
Thank you, and thank you for the invitation. I'm sorry I cannot be there in person. I'm actually in South America right now. So I'm going to talk about equivariant machine learning, and we heard about it in the previous talk, so a lot of the motivation is already given. I will I think that there are some things that will complement very nicely with what Max Welling discussed. So hopefully it will make sense to you all. And if you have questions, please ask. So I'm going to talk about different series of papers, some of them about graph neural networks, which are in collaboration with Zendao, Lei, and John Bruna from NYU, and then other ones that are related to equivariant machine learning for physics in collaboration with David Hogg, Keister Fischer, Wei-Chi Zhao, and Ben Bloom-Smith. So I think I don't need to introduce the motivation for implementing symmetries in deep learning after the talk by Max Welling, but I'm just going to say that there is some heuristic explanation that tells you that one of the reasons why deep learning is so successful is because it kind of captures the symmetries that natural data has, like natural images have some translation and rotation symmetries that are captured by these convolutional filters applied in the same filters in different locations of the image. And also there's an heuristic explanation of why recurrent neural networks exploit some sort of time translation that is apparent in text. But I'm not going to discuss a lot of the maybe not exact symmetries, but I'm going to focus more on exact symmetries. And those are the symmetries that are implemented by graph neural networks in particular. So graph neural networks are classes of functions defined on graphs so that they are invariant or equivariant with respect to node relabeling. And that was discussed in the previous talk. So the idea is that if I have a graph and I represent this graph as an adjacency matrix, I'm making a choice of the order of the nodes in the adjacency matrix, and whatever function I learn needs to be agnostic to that choice. And so one way of implementing something that satisfies that property is by doing message passing, which doesn't even see any adjacency matrix. It's just like there's one function that is a message function that is learned and is applied to every node, and every node sends a message to their neighbors. And then every node has an aggregation function that is also invariant with respect to relabeling, where aggregates the information from the nodes, the neighbors, and then that's implemented as a neural network. That's like the most basic neural network architecture. So this is called weight sharing, the idea of using the same function for every node. And that was discussed in the previous talk. And a lot of times, if you define these functions naively, you'll see that the classes of functions that you can express in that form are limited. So understanding what are the expressive power of graph neural networks is a very active line of research right now. So just to recap, I'm going to talk about invariant functions and equivariant functions. So invariant is a function that if I apply a group action to all my input vectors, then the function doesn't change. And equivariant also requires that the group acts on the codomain of the function, and you need that h of g times x is equal to g times h of x. The action could be different in the domain and in the codomain, but the group is the same. And yeah, so two classes of functions, and I have a small example. It's not necessary to go through it, but say you have a graph and you're looking for the length of the shortest Hamiltonian path. That is a scalar. It's just a number. It's just a one-dimensional number, which is invariant. It doesn't depend on the representation of my graph as an adjacency matrix. But if I'm looking for the actual sequence of nodes that I would visit in order to get this shortest length Hamiltonian path, then that is going to be equivariant, because if I change, say, the order on the adjacency matrix between the green and the yellow, then the solution needs to change accordingly. So this example in these graphs, the length of the path is an invariant function with respect to the action of permutations by conjugation, and the actual path is an equivariant function with respect to it's a function that goes from like Rn times n to Rn, which is the vector of the nodes, and it's equivariant with respect to the action of the permutations by conjugation on the input and by multiplication on the output. That's the example. Good. So another example of equivariant functions is spectral methods. So if I have a matrix and I take the top or any, like say the top eigenvectors, the first eigenvector, second eigenvector, third eigenvector, then if I apply a permutation on the rows and the columns, like if I apply this permutation, then the corresponding eigenvector will have the same permutation as well. So that's the reason why spectral clustering works, for instance. And this idea that we have some class of functions that are permutation invariant is a basis for defining other types of graph neural networks that are not depending on this message passing idea that I just told you earlier. These are called spectral GNNs, and the first time that they appear is in the context of community detection in a paper by Zendao, Chen, Li Shali, and Joan Bruna in 2017. And basically what they want to parameterize a class of functions that is equivariant, and they do it by, and then they can perform learning on that class of functions. And they do it by constructing some sort of regularized spectral method. So given a graph G, one can construct the adjacency matrix, and then a set of operators that depend on the graph. So the identity, the degree, adjacency matrix, and then powers of the adjacency. And then we can say, okay, I'm going to learn a regularized spectral method, which is going to be a linear combination of these operators of the graph. And then I'm going to take the top eigenvector, or like the top k eigenvectors of this regularized spectral method. If you are familiar with the work on community detection using like this optimal spectral methods, then like the Bethe-Hessian spectral methods, this idea of using learning methods in this form comes from this specific work in community detection. And so once that you know that you have this parameterization for the class of functions, then you can think of unrolling it into a graph neural network, or unrolling it into a neural network by considering that, say, if you want to take the top eigenvector, you can just do a power iteration, and you do like t steps of this power iteration, and then you unroll this as a neural network with each of the layers corresponding to one iteration of your iterative method. And then you can have over-parameterize that, for instance, changing the parameter that you learn in each of the layers of this implementation of this iterative method. And instead of learning, say, a one-dimensional parameter, you can say that you are learning an embedding in each of the layers to dimension dt, and just over-parameterize it in that form. So that's one way of doing it. Note that this parameterization for this class of functions on graphs has the property that it doesn't depend on the number of nodes that you have in your graph. So the number of parameters is something that depends on like these sizes of these embeddings, but it's independent of the number of nodes. And so you can train a neural network on like 100 nodes and then apply it to 200 nodes. And there's some mathematical results that analyze the transferability of objects of this form. But that's just one example. And in this talk, I'm going to discuss some other forms of equivariance that are not necessarily the equivariance with respect to permutations, but other groups, like some of the groups that Max Welling was describing earlier, like the orthogonal group, Euclidean group, which also includes the translations and rotations, etc. And this is a particular case of this physics-informed machine learning, where one wants to incorporate the physical constraints of systems that the laws of physics obey in order to make predictions. So if you want to predict particle simulation and you know that the particles have interacting forces that are equivariant with respect to rotations, then you want that your prediction model also obeys these laws or these properties. So in particular, I'm going to focus on groups that show up in physics. So the orthogonal group, the rotations, translations, the Lorentz group, which includes boost, and the Poincare group, which is rotations, Lorentz transformations and translations, and also the permutation group. And the idea is that the conservation laws, if you have a system that satisfies symmetries generated by local actions, then there corresponds a conservation law, and this is a deep result by Emmy Noether in like 1915, which has deep implications in physics. So in these examples that I'm going to explain how you can implement it from like and what is the mathematical theory between many of these systems that implement these equivariances. So in this case, I have this like particle simulation, and say I want to predict the dynamics from the initial conditions. And my initial conditions are the positions and the momentums of the particles. And I want to predict the positions and momentums of particles in the future. And I know that if I apply a rotation to my inputs, then the predictions will rotate accordingly. And basically that's the equivariance that I care about in this specific example. So, and this was discussed before, how are symmetries then implemented? Well, data augmentation is one of the ways to implement the symmetries. Also, you can implement symmetries by having some sort of loss function penalties. Like if you know that some symmetries correspond to, say, the conservation of energy, you can have a penalty term that preserves the conservation of energy, and that implicitly will try to enforce certain symmetries. But what I'm going to discuss today is this architectural design approach, and a lot of it was already discussed by Max Welling, and he has a lot of work in this area of implementing it with weight sharing or this group equivariant convolutional networks, so like these steerable CNNs. And then I'm going to explain other approaches that weren't explained in detail in the previous talk, I believe. So hopefully it will complement what was already said. But basically, one question is like, how do you parameterize these symmetry preserving functions? And I'm gonna go into this in like 2 slides. But before that, I wanted to mention that why would you want to implement the symmetries via this architectural design? And I think in the previous talk, there was a question of how much do you gain in terms of sample complexity when implementing the symmetries. And I wanted to mention that there's some work in this direction, and I think this question is not completely answered yet, but there's some work by May Mesiakewicz and Montanari from 2021, where they actually look at the random features model, and they do look at the random feature model satisfying certain symmetries, and they have a generalization error in terms of what is the size of what is the dimension of the space of functions divided by the dimension of the space of functions that satisfy the symmetries. Does that make sense? So there's like, if you're restricting yourself to like spherical harmonics of degree k, then you look at the spherical harmonics of degree k that satisfy the symmetries. Those two spaces are linear spaces. You can look at the dimension of these spaces as linear spaces, and you can compute a bound on the sample complexity of the problem in terms of the quotient of this dimension of these two spaces. There's also a paper by Vietti and collaborators, and also other papers that analyze similar settings, but they're all restricted to like finite dimensional spaces of functions, as far as I know.
I have a question, Soledad.
Yeah.
Can you hear me? So it's a general question about enforcing symmetries. So is the idea that you want to enforce symmetries throughout the computation, or just at the end of the computation? At least coming from theoretical computer science, there are very famous examples of functions which are symmetric. And if you enforce symmetry throughout, then the smallest circuits or whatever that can compute these functions can have actually a huge size compared to non-symmetric circuits. It seems like even when there is symmetry, non-symmetric computation can help. So I just want to get your perspective on this.
Yes, that's a good question. So the way it's done, and I think I'm going to explain that in the next slide, a lot of these works implement the symmetries throughout. Like in each, say, they consider a neural network that is like several layers, and each of the layers satisfy the symmetries, and also they have restrictions on the activation function so that everything satisfies the symmetry. So at each layer of the network, the symmetry is satisfied. There are other works, like the one that I wanted to present, that basically construct features so that the learning is invariant by definition on those features. So they don't necessarily implement the symmetries throughout. And I believe the second approach is simpler, and it's universal, so you can universally approximate every function for some specific groups. So I think, yeah. So I guess both ways exist. But sometimes, and I think something that is important is sometimes enforcing the symmetries can be hard. Like basically you restrict the class of functions where you do the learning to functions that have the symmetries. And then sometimes it's hard to parameterize the class of functions that have the symmetries. And sometimes you can parameterize the functions that have the symmetries, but not all of them. You design an architecture, and then it does satisfy the symmetries, but it's not expressive enough. And that's something that has been observed in the context of graph neural networks a lot. And does that answer your question?
Yeah, I mean, I guess to your second point about enforcing symmetries can be hard computationally. Yeah, I mean, if you have, let's say, two bodies system in physics, which you can describe it using 12 coordinates, 3 for velocity, 3 for position for each of these two particles. I mean, in the Euclidean space, there are simple laws, Newton's laws, right? But if you want to go from there to Kepler's laws, which involve maybe 2 parameters, there's a whole bunch of quotienting that you have to do. And that quotienting then forces you to do move in these quotient manifolds, which I think can be pretty hard because you don't know even straight lines what they are so easily. So is that what you're referring to?
Yes, and I think I have a slide about what you're referring right now. Like what is the invariant theory for these classes of functions, like invariant polynomials. And you have like the primary invariants and the secondary invariants, and you can, if you have a parametrization for both, then you have a nice parametrization. Yeah, but I'll get there soon. So just one thing that I wanted to mention regarding the expressivity of the graph neural networks It's like, okay, these graph neural networks we saw, they have to learn functions on adjacency metrics of a graph so that they are permutation invariant with respect to this conjugation. And so there's very famous papers by Xu and collaborators in 2019 and Chris Morris and collaborators at the same time. And basically what they show is that if you do just like a naive message passing neural network, then what happens is like there are some graphs that are not distinguishable. And this is basically the same graphs that are non-distinguishable, like they're pairs of isomorphic, non-isomorphic graphs that for every message passing neural network, the function that you obtain for both graphs is the same. And this is in connection with this, with the graph isomorphism problem. And basically the characterization says that these two graphs can be distinguished by the message passing neural networks, if and only if they can be distinguished by the linear programming relaxation of the graph isomorphism problem, which is basically the optimization in the Birkhoff polytope. So just like this, I guess, is here. So if you implement this naively, then you get something that is very trivial. And so what we did in our paper in NeurIPS 2019 was to look at different classes of graph neural networks and characterize their expressive power in terms of their ability to distinguish non-isomorphic graphs. And we have like a comparison between different classes of graph neural networks. And in particular, most of them that are used in practice are actually not expressive enough. And there's some classes of functions that can be expressive enough, but computationally you cannot use them because they're very expensive. So I guess that of course you don't expect to solve the graph isomorphism problem with graph neural networks. And this is kind of telling you that a lot of these functions are not really working very well. So there's some other approaches that basically look at these message passing neural networks as functions that transform signals on graphs, and those ones tend to be more expressive. Like instead of just like a function of a graph, is like a function of a function defined on a graph, and then those ones tend to be more expressive. And we can also show that these GNNs cannot count many substructures if they are defined in this naive way. So I guess, yeah, that shows that implementing symmetries is not always working very well. At least, yeah, but now there are more directions that can have expressive functions on graphs, but just like you have to do it with care. So in general, just not necessarily for the permutations, but in general, if you have any group action, how do you implement these equivariant functions on graphs? On any group action on vectors. So the typical approach, this is called like equivariant machine learning. There's some papers by Risi Condor and also by Maron that basically describe this approach that is based on the feed-forward neural network, but you restrict the linear functions to be equivariant. So basically you have your input is B, and then you have a linear function, and then a nonlinear activation function, and then linear, etc. And you ask that each of these linear functions are equivariant. And so since when you restrict to that, typically you don't get a lot of functions that are linear and equivariant. In order to have something that is more expressive, what you can do is you can consider the linear functions that take tensors of inputs and then output tensors of vectors, right? So instead of doing a linear function from RD to RD that is equivariant, you do like a linear function of RD to the K to RD to the K. So that is equivariant, and you think of the action in this tensor to be the action in each of the orders of the tensor, in each of the dimensions of the tensor. So basically, Q acting on this tensor is equal to Q acting in each of the dimensions of the tensor, right? And now the question is, how do you parameterize the functions that satisfy those properties? So, and also how do you find the compatible activation functions? And so one approach is by this paper that is actually by Mark Finsley and Max Welling and Andrew Wilson, is by solving a system of linear equations. The idea is that the linear functions that are equivariant is a linear space. So you can, if you have enough constraints that you can express in this form, then you can solve a system of equations and find a parameterization, find the basis of this linear space, and then parameterize them using that. So you can learn the parameterization of the space of equivariant functions on the fly. The other approach is this irreducible representations approach that was mentioned in the previous talk. The idea is that if you want to parameterize linear equivariant maps, then this is equivalent to find linear maps between the representations of the spaces. And so you can, once that you have the representation of the space, you can decompose this representation in terms of irreducible representations. And once that you have the irreducible representations, the maps between these two irreducible representations is very easy. It's just like the identity or zero, or a multiple of the identity or zero. So basically, you will need to take the representations and reduce it in terms of the irreducible representations, decompose it. And this, so in our case that we were looking at these tensors products of my inputs, then I will need to write a tensor representation in terms of irreducible representations. And in order to do this, you need to compute something that is called the Clebsch-Gordan coefficients, which is known for some groups, but it's not known in general, or they're sometimes hard to compute. But I must say that there's some implementations that actually work for SO3, and I think the two that I know are, the first author for one is Thomas, and the first author for the other one is Fuchs, that actually implement these irreducible representations for SO3, and they have all these equivariant networks that are actually defined on the continuous group, and they use instead of writing the tensors, they write it in terms of the spherical harmonics, so they don't have to write a very high order tensor, and it works. And this approach is proven to be universal for SO3 if you can consider arbitrary high order tensors. So if you can consider the spherical harmonics of degree k for arbitrary k, then this approach universally approximate all SO3 equivariant functions. So that's the way they do it. So what I wanted to present today is my work that is going to appear in UNEV's next week, which has a simpler parameterization of equivariant functions with respect to groups that are specific groups that are used in physics, in particular rotation, parity, boost, and in any dimensions. And it doesn't, the approach is very simple, and it doesn't depend on the dimension of the space. The idea is, okay, given n vectors in Rb, I want to parameterize invariant functions, and given n vectors in Rd, I want to parameterize vector equivariant functions, so the output is a vector in Rd. And the groups that we consider are the orthogonal group, rotations, translations, Euclidean group, Lorentz group, Poincaré, and permutation. And the action are the actions that you would expect. So just like when you act with one vector in with one rotation or matrix on a sequence of vectors, it means that you act in each of the vectors with the same rotation. And so the mathematical background for that is very simple. It's called the the fundamental theorem for invariant functions for OD, which is something that shows up in a book by Villar from in like the beginning of the 20th century. Basically what they show, and it's very easy to show, that a function from RD to the n to R is OD invariant if and only if you can write it as a function of the inner products of the input vectors. Like the reason why this holds, one direction is obvious, because if I apply a rotation to my input vectors, the inner products don't change. And the other direction is by considering, given the matrix of inner products, M, I can recover the factorization of M as L transpose L using the Cholesky decomposition. And then that factorization is unique up to all the transformations. So basically you can recover the input vectors up to orthogonal transformations, which is what we wanted. From the physics point of view, you can write this as like all scalar quantities can be written in this Einstein summation notation, which is basically taking inner products of your outer products and inner products of your input vectors. The same thing holds for the Lorentz group, but instead of looking at the inner products of the input vectors, I will need to look at this Minkowski inner product, which is defined in this form. So the time component multiplies and then minus the inner product of the space. Right. And a very similar thing will hold for SOD, but you will need to take into consideration the determinant. So it's a little bit more complicated. You will have more terms, but yeah.
So I guess this can be generalized to any Riemannian, pseudo-Riemannian space, or I mean,
depending on the group.
Okay.
Yeah. Mm-hmm. Yeah. Mm-hmm. Yeah. But yes. So do we need all the inner products for parametrizing all these functions? And the answer is no. And the reason why is maybe you can think of it in terms of this low rank matrix completion idea, that actually you don't need to know all the inner products to determine the vectors. So even you don't need to have like n squared features. Say that you have like your input is n squared in n vectors in RD, and then now your features are going to be like n squared scalars, but actually you can use fewer of these n squared features. Say like if you have these observations from your matrix, this is enough to determine your matrix because your matrix is rank B. So you could have a nice design of scalars where you don't make your parametrization go to like n squared number of features, if you really care about the efficiency of that. So this can be generalized very easily to equivariant vector functions. And the idea is the following. Given a function of n vectors in RD that outputs a vector in RD, this function is OD equivariant if and only if you can write it as a linear combination of the input vectors. So H of these vectors is going to be a linear combination of the input vectors where the coefficient functions are any OD invariant scalar function. And so then this suggests an architecture of this form. Say, I have input vectors, then I construct these scalars, and then I'm going to learn these functions on these scalars, these functions over here, and then I'm just going to construct the output as a linear combination of that. This parametrization is universal. Like any function that is equivariant, vector equivariant function with respect to OD can be expressed in this way. And every function that is expressed in terms of these scalars in this form is going to be equivariant. So that simplifies the entire parametrization of the space of OD equivariant functions. And the proof, and this doesn't require to know the reducer representations, and it doesn't have like these layers where like you have to restrict in every layer to be equivariant. you can just say your function of the features is equivariant. And I must say that in the last like 5 minutes of Maxwell's talk, he had a definition of something that was like these EN networks, where he wrote some functions of like the distance of the pairwise vectors using using graph neural networks. So he had like a function of like the norm of the distance of the difference between some vectors. And if you look at it, actually you can see that it has this form in some way, because you can write the distance, the norm of the distance between the two vectors as in terms of scalars, and it does have this form. So yeah. So the way you prove that this parametrization is sufficient is by showing that if you have an equivariant function, then with respect to OD, then the function needs to lie on the span of the inputs. That's not true in the case of SOD, for instance. In SOD, you can have equivariant functions, like for instance, the cross product of vectors like this, that is not in the span of the inputs, but you can add those. Those are the only ones that actually can show up in codimension 1. And once that you have that, then you know that your function h can be written as a linear combination of your input vectors with some functions, but the functions are defined like set theoretically, so you would need to like use the axiom of choice to construct them, or like there would be like annoying functions. But actually you can prove that if h is a polynomial, then you can write these functions to be polynomials as well, can be chosen to be polynomials. They may not be unique, but because you may have more vectors than the measure of the space, but you can choose, if this is a polynomial, you can choose these ones to be polynomials, and polynomials are universal, so then that makes it nice. Okay, so I have maybe 10 more minutes or 15 more minutes, so maybe I can show this example. So this example is the electromagnetic force law for a particle, for particles. Like my test particle here it has charge q, position r, and velocity v, and I can just write this force in these terms. So you think, okay, this force is actually not written in terms of the scalar products, but there exists, because you're using like these cross products here. But there exists a reparametrization of this function, like using the property that you can write this sequence of cross products as in terms of scalars, and then you can rewrite this function so that actually it's in this form. So every equivariant function that you see in physics, you can write it in this form, and that's one example. However, you may say this formulation that you have here is not as nice, because it's not a field formulation anymore, but still, yeah, you are not able to isolate your test particle from this thing, because you will have a sum that depends on this, the coefficients depend on this test particle. But just saying that it's possible, though it doesn't always give you the best parametrization of the function class. This is very easily extendable to translation equivariance, as you may imagine, because you can think of like differences on the input vectors. And something maybe interesting is that you can write permutation equivariance as well. Like say, if you have a function h that is OD equivariant, and also permutation invariant, meaning that if I apply a permutation to the input vectors, then the function doesn't change. Then you can write this function as a linear combination of your input vectors times this function f, that is the same for everyone, but f sees the vector that it's multiplying differently than everyone else. So that you can think of it as a form of message passing, like the EN message passing method that Max Walling was describing before. And it's easy to implement with graph neural networks that do message passing neural networks. And for general groups, and that's something that that you just asked me, was what do you do for general groups? Basically, we know what we want to do is we say that G is a reductive group. So matrix groups are in this class. So we know that the algebra of invariant polynomials is a graded Cohen-Maclaurin algebra. What does it mean? It means that you can write every element of my ring of polynomials in terms of primary invariants and secondary invariants. So these elements are going to be polynomial of my primary invariants multiplied by some secondary invariant for each. So there exists a decomposition of my X in this form, right? And so there exists this primary invariance and secondary invariance. So every element X has a unique decomposition in this form. And this, what I just did before for like the orthogonal group, is just saying that for the orthogonal group and D greater than N, and this D greater than N is just a technical thing because we want the decomposition to be unique, but you can, if you don't want uniqueness, you don't care about that. The F1s through Fn, so the primary invariants are just the scalar products, and the secondary invariants are trivial. And so that's why we can write every function in these terms. But if you want to go to other groups, then you can just compute the primary invariants and the secondary invariants and find a very nice parametrization of the polynomials, the invariant polynomials. But this is especially when you have combinations of groups acting in different ways, this is not known. So for instance, something that I have a collaborator who did his PhD in invariant theory, and we discussed, for instance, if we want to have a parametrization for the graph neural networks, the permutation, the action by permutations or by conjugation, where are the primary invariants and where are the secondary invariants? And actually for those, I believe that they are not known. And sometimes they are known, but they are not, they are large, they don't scale well with the size of the problem, so it's not useful for machine learning. So basically that's it. So to finalize, I'm going to show you a couple of numerical examples, and there are toy examples. And so basically, and actually I must say that this drawing is from Mark Finzi, where they present this in this very nice paper that they have that is called EMLP. They have their code on GitHub and it's very nice. They implement the equivariance using this set of constraints, linear constraints that they solve on the fly. And what we do is we apply our model to their setting, and we just take the same prediction tasks that they have in their paper, and then we use our model and we show how that performs. And so here we have a double pendulum with springs, and the data are going to be positions and momentums of particles. And we know that the system is Hamiltonian. So there's a conserved quantity, which is the kinetic energy plus the potential energy. And we are going to model this system as O3 equivariant. And the reason why we can model this system as O3 equivariant is because we put the gravity vector as an input to my learning function. So if I change everything and I rotate the gravity vector as well, then the rotation, the system is equivariant. So this is what I'm learning. Given initial positions and momentums of first mass and second mass plus gravity vector plus time, I'm going to learn what is the system look like in this delta t time step. And the way we can do this is by two approaches. One is called this neural ODE approach, which basically, given the observations, you learn a differential equation that your data satisfies. And then you use an ODE integrator to make your predictions. And the other approach that we use is this Hamiltonian neural network, where we learn a Hamiltonian and then we use a Hamiltonian integrator, which you would expect that it would perform better. And so how our model fits here, which is basically both the Hamiltonian or the neural network that we are learning it as a function of the scalar products. So it's going to be equivariant just because it's just a function of the scalar products, and we proved that that's equivariant. And so we show that actually when you implement this equivariance, we obtain smaller errors than this EMLP in the predictions for the groups that they don't consider all three equivariants. They consider O2, SO2, D2, and D6. And also they consider this MLP, which is not equivariant at all. So maybe that answers one of the questions that you had before of like implementing this equivariance, how well does it perform? Like how much do you gain? Well, computationally, this is one example where you gain quite a lot by implementing the equivariance. And here we're implementing two symmetries. We're implementing the equivariance and we are implementing the Hamiltonian symmetry when we do this Hamiltonian neural network. And in these phase diagrams, we can see that actually the prediction with the Hamiltonian is much closer than the prediction that doesn't assume the Hamiltonian, just for that model. So it's, yeah. I have another numerical example showing the error as a function of the size of the training set for a simple like toy example as well. And for different models, including like MLP and MLP with data augmentation and SO3, maybe it's too small to see, but yeah. So to end my talk, I'm going to say that the goal that I had was to enforce exact symmetries machine learning models because there is this idea that they improve the sample complexity and they have smaller generalization error. We saw in the case of the graph neural networks, which is the ones with permutation equivariance, we can characterize the expressive power of graph neural networks via the graph isomorphism problem. And in the second part of my talk, I described the symmetries from classical physics, and we have a very simple characterization of all equivariant functions that are equivariant with respect to these physically relevant group actions, and there's ongoing work to have it for more general groups. And I guess some open problems that I'm interested in is like something that I asked before during the talk of my Maxwelling, like kind of including dimensions and unit symmetry with that equivariance, would that be something interesting? And yeah, I don't know. And maybe something that I think is very interesting is incorporating the multi-scale information, like instead of doing message passing between pairs of nodes in a graph or pairs of particles, if you had like a hierarchical decomposition of the space, like an FMM or a KD tree, can we implement this in a more efficient way and make it scalable for real applications? And I have collaboration with people that are working on the application side, in particular in astrophysics. David Hogg is one of my collaborators in this paper, who is at the Center for Computational Astrophysics at the Simon Foundation in New York. And also I have collaborations in computational biology that could benefit from this equivariant formulation of of these functions. So that's it. This is the end of my talk. And if you have questions, I'm very happy to answer.
All right. Thank you, Soledad. That was great. Are there any questions? Got a question?
Yeah, thank you very much. It was a very nice talk. So I had two questions. So one is related to the role of n. So you say that you have vectors which are RD to the n. So in your example, of course, n was very small, but so are there examples where it's important to have n that goes to infinity or something like that? So when n is very large, and what is the behavior, again, as you mentioned, what is the behavior of the space? Are you lowering in some sense the dimension of the parameter, so the number of parameters that you're looking? And this is the first question. And then the second question, yeah, now I don't remember the second question, so let's go just with the first question. Sorry.
Okay, so n, yes, in practice, n can be very large. So something that I haven't done, but I'm working on, is to try to use this, for n-body simulations. What people use in practice is these fast multiple methods that are based on multiple expansions, and basically they take the space and they have like a decomposition of the space in like these like small quadrants. So then if I have a particle here, instead of looking at all pairwise interactions, I will look at the pairwise interactions to like the center of the panel the panel that is very far away. That's like the fast multiple method. I don't know if you are familiar, but basically that's what it does. So instead of having n square messages, you have like n log n messages, and that's and it approximates quite well. So I think in order to make it scale, I will need to do that for sure. And I don't know how to combine the scalar formulation with the FMM, the multiple expansion, but I'm pretty sure that there is a way. I'm pretty sure, because they look very similar. So I think that there should be a way to combine both. Yeah. So instead of looking at all, and then I guess that's also a question, like instead of looking at all inner products, maybe I want to look at a set of inner products which is permutation invariant and also universally expressive, because typically in these particle simulations, all the particles are interchangeable. So the function would be invariant with respect to permutations. So in that sense, for instance, if I consider just like the sum of the inner products, that's invariant, but that's not universal. So I will need to take like the sum of the inner products, and then the sum of the squares of the inner products, and the sum of the cubes of the inner products, etc. And yeah, and I don't know how that will perform.
Okay, we have one more question.
Maybe this is related to the ongoing work about general groups at the end, but I was wondering, how do things change if instead of changing the group, you just have a different group action, as opposed to, like, I think the examples towards the end had OD just acting on tuples of vectors by multiplication. What if you have kind of other actions of OD? Is that easier to understand than just going to a general group?
No, it's the same, because the action is everything. Like, so for instance, say if you have the permutations acting by multiplication, that's very easy. If you have the permutation acting by conjugation, that's much harder. So it's the same group acting differently, and then the space of invariant functions changes completely. So yeah, so I guess that here I should have said parameterization for general groups and different group actions, or different group actions. Like this depends on the action. The ring of invariant polynomials depend on the action. Mm-hmm.
Thank you.
Yeah, I guess I should leave this. Mm-hmm.
Okay, sorry, it's me again. I remember the second question. So Actually, so one was more of an observation. So what you do when you're saying that there is a permutation invariance on the on your vectors. This reminded me of some mean field approximation for ODEs when you have several interaction between multi-agents, but the interaction is the same between them, and there is and so in the end what you get is that the velocity that one agent feels depends not on the positions of each of them, but you take the measure associated with the sum of the Diracs. In that way, it's already independent. And so I was wondering if and this is again, this is in the viewpoint of letting n goes to infinity. So this was just an observation. And the other question instead was on the example that you gave of the pendulum, of the double pendulum. So the data that you have is just the final time, or you have the trajectory?
Yeah. So in the double pendulum, in my training set are of the form of these, but not just at time 0, but I have like time 0, 1, 2, and 3, and 4. So I have four times of my trajectory for a small delta t. And then my prediction is like to extrapolate the trajectory to like 300 time steps. So here, if you look at these, sorry about that. If you look at these phase diagrams, maybe it will be easy to see here. So the first 5 points are the training points, and then the rest is the trajectory that is predicted by the model. Does that answer your question?
Yeah.
So if you go like at the end, you see that actually there's one that is one prediction that is very far. The prediction with the neural ODE is much farther than the prediction with the Hamiltonian neural network, which you would expect because the Hamiltonian already encodes this time, like the Hamiltonian symmetry.
Great. I don't see any questions online. So with that, I think we'll wrap up, and thank you again, Soledad. That was a great talk.
Thank you.
Okay.
You get to end on time.
Yes. Thanks again for that.
I think with this, we come to the conclusion of the workshop. So thank you so much to all the participants, to all the speakers, and also, my co-organizers, Michael Walter and Asia Wilson. And last but not least, the Simon staff, which has been incredibly helpful in making this happen. And hope to see you all somewhere soon.
Thanks, Najib.
Where are you all at? Are you in Boston?